In the previous video, we have learned about sources and lines and also current carrying conductor. So now we want to apply what we have learned to solve a few examples. Example 4.2, we have two straight wires which are placed parallel to each other carrying the same current I. And then we have to sketch the magnetic field line patterns for both wires. So for A, when the currents in both wires are in the same direction, and then B, when the currents are in the opposite direction. Okay, you can start off by drawing two straight wires. The currents that are flowing through the wire are both in the same direction. Using right hand grip rule, your thumb will be pointing in the direction of the current and you will get magnetic field which is counterclockwise, which is drawn like this. For wire 2, you will get the same direction of magnetic field because the current is still pointing upwards. Then draw a line connecting the magnetic fields of both wires. And you can also draw from another point of view. If you are viewing from above, the diagram will look like this. And for B, we still have two wires, but the currents that are flowing through both wires are in the opposite direction from each other. Wire 1, you will have current which is going upwards, so magnetic field will be counterclockwise. Wire 2, you have current going downwards, so magnetic field will be clockwise. And then make sure to draw the lines in the middle because both fields are going in the same direction. And then the alternative method is to draw it from above. So you can draw the same diagram and then you can use the dot and cross to represent the current and then draw the magnetic field lines and you will get something like this. Let's go through example 4.3. We have a long wire X which carries a current of 50 ampere. It is placed parallel to and 5 cm away from a similar wire Y which carries a current of 10 ampere. And then we have to find the magnitude and direction of the magnetic flux density at a point midway between the wires. And first is for when the currents are in the same direction and another one is for when the currents are in the opposite direction. So you can start off by drawing two wires, wire X and wire Y. The currents that are flowing in both wires are flowing in the same direction. And then the two wires are separated by a distance D. And there is a point A in between them. And the distance of point A from X is Rx and distance of A from Y is Ry. So what we want to do is find the magnetic flux density B at point A. Okay, first use your right hand grip rule and then find the direction of the magnetic field for wire X and Y. So for wire X, the current is going upwards and then the magnetic field will be counterclockwise. And then to get direction of B at A, you have to draw a tangent to the curve and then you will get B to this direction, which is into the page. And then for wire Y, the current is also going upwards, so you will still have a magnetic field which is counterclockwise as well. And to find direction of BY, once again just draw a tangent line at A and you will get BY in this direction which is out of the page. You can also draw it as if you are viewing it from above, so the current will be represented by this sign, which means that the current is going out of the page, and then there is point A in the middle between wire X and Y with distance Rx and Ry. Then you have to draw the direction of Bx and By. Imagine you have a magnetic field which is viewed from above and then there is point A on that magnetic field in which you want to find the direction of B. So B is the tangent to the line and you will get B which is upwards. And for By, the direction will be downwards. So D is already given in the question which is 5 cm. And then you can see that D is actually equal to Rx plus Ry. And since point A is midway between the two wires, that tells us that Rx is actually equal to Ry and they are also equal to D over 2. So you will get their values to be 2.5 cm or 2.5 times 10 to the power of negative 2 meter. To find magnetic flux density at point A, we can use the formula for straight wire. So B for straight wire is B is equal to mu naught I over 2 pi r. And in this case, we want to find Bx, so Ix and Rx. Mu naught is a constant, which is 4 pi times 10 to the power of negative 7 times by the current in X, which is 50 ampere over 2 pi. And Rx is 2.5 times 10 to the power of negative 2. The answer is 4 times 10 to the power of negative 4 Tesla. And then you have to include the direction of Bx as well. So Bx, if you refer to the first diagram, if you have a page, Bx will be going into the page. So the direction should be written as into the page. Or if you refer to the second diagram, then the direction will be upward. To calculate By, we use the same formula, mu naught Iy over 2 pi Ry, and then substitute in the values. So 4 pi times 10 to the power of negative 7 times 10 ampere over 2 pi, and Ry is 2.5 times 10 to the power of negative 2, and you will get By equal to 8 times 10 to the power of negative 5 Tesla. So you have to determine the direction of By as well, and By is going out of the page or downwards. Okay, we have Bx and By, so what do we do now? So actually we want to find the resultant magnetic flux density B at point A. If we refer back to this diagram, we can see that we have both Bx and By. So what do we do here? We find the sum of Bx and By. Doing this will give us the total magnetic flux density at point A, in which Ba is equal to Bx plus By. However, we have to consider the sign for Bx and By by looking at the direction of their magnetic field. Out of the page will be positive and into the page will be negative. So Bx is into the page negative, By is out of page positive. So write down Ba is equal to negative Bx plus By, and then substitute in the values of Bx and By to get Ba, which is negative 3.2 times 10 to the power of negative 4 Tesla. Question asks for magnitude and direction, so you have to include the direction as well. So looking at the sign of Ba, it is negative, which indicates that Ba is going into the page. But you will also have to note that the question is asking you to find the magnitude of B. So for magnitude, you have to use the modulus sign for B, and the answer will always be positive. So for this question, you have to rewrite your final answer in the modulus sign, and then write it down with a positive value, and then write the direction as well. Now for question A2, we want to find the magnetic flux density at A if the currents are now flowing in opposite direction. We can solve this using the same method as in question 1, in which we find the direction of the magnetic field at point A. So we will have Bx and By, and for this question, our Bx will be pointing into the page, and By will also be into the page. And you can also draw this from above. Rx is still equal to Ry, which is 2.5 centimeter, and then we have to find Bx using the same formula, mu naught Ix over 2 pi Rx, and then substitute in all the values, in which we will get 4.0 times 10 to the power of negative 4 Tesla, and then we have to find the direction of Bx, which is into the page or upwards. And then we have to find By using mu naught Iy over 2 pi Ry, and substitute in all the values, in which By is 8 times 10 to the power of negative 5 Tesla, and the direction for By is also into the page or upwards. And then we have Bx and By, so now we have to find the total or the resultant magnetic flux density at point A. So we just have to find the sum of Bx and By. So B at A is equal to Bx plus By, and then we have to look at the sign of Bx and By. So both are into the page, so Bx is negative and then By is also negative. And then substitute in the values of Bx and By to get Ba, which is negative 4.8 times 10 to the power of negative 4 Tesla. And then you have to include direction as well. So because Ba is negative sign, so it is actually going into the page. Similar to the previous example, you have to rewrite your final answer in a modulus sign. So you will get Ba, which is a positive value, and then include the direction as well. For question B, the currents are still in the same direction, but there is a point between wire X and Y in which the magnetic flux density will be 0. So how far from X is this point? Okay, for B, we have wire X and Y, currents are in the same direction. However, we have point C, which is not midway between both wires. So basically, Rx and Ry are not the same. And then we have to find what is the distance of point C from X, which is basically Rx, when the magnetic field density at C is equal to 0. At C, we have Bx, which is into the page, and By, which is out of the page. And then you can draw this like this, using the dotted circle to represent the current, and then you have C in between them. So you will get magnetic field Bx and By, which is one is going upwards and then another is going downwards. And as you can see from this diagram, Rx plus Ry is actually equal to D. So D is Rx plus Ry. Let Rx be R and Ry will be D minus R. Then the question has mentioned that the resultant magnetic flux density at point C is 0. So we know that B at C is 0. And BC is actually the sum of Bx and By. And then because Bx is going into the page, Bx will be negative and By is going out of the page. So By will be positive. And BC is equal to 0. So from here we can see that Bx will be equal to By, where Bx is mu naught Ix over 2 pi Rx and By is mu naught Iy over 2 pi Ry. Start off from Bx is equal to By. Bx is mu naught Ix over 2 pi Rx equal to mu naught Iy over 2 pi Ry. And then you can cancel out mu naught and also 2 pi. So we are left with Ix over Rx equal to Iy over Ry. And then substitute Rx is equal to R, and then Ry is equal to D minus R. And we will get Ix over R equal to Iy over D minus R. So now we can substitute in the values of Ix, Iy and also D. D is 5 centimeter. Solve this to get R, which is 4.2 times 10 to the power of negative 2 meter. Okay, example 4.5, we have a question on circular coil. So the circular coil has diameter 10 centimeters. So this is D. And then it has 500 turns, which is capital N. And the coil carries a current of 2.5 ampere. So this is I. And the question wants us to find the magnitude of the magnetic field at the center of the coil. Okay, so B. So to answer A, list down all the information that you have. We have the diameter. So from the diameter, you can find the radius, which will be 5 centimeter. To find B at the center of the circular coil, we use the formula. B is equal to mu naught Ni over 2R. And then substitute in the values of mu naught, which is a constant, and then N is 500, I is 2.5, divide by 2, and the radius is 5 centimeter. Convert to meter first, and then you will get the answer 1.57 times 10 to the power of negative 2 Tesla. For question B, we have a solenoid with a length of 1.5 meter, and then diameter 2.6 centimeter, and it carries current of 18 ampere. And then the magnetic field inside the solenoid is 2.3 millitesla. So B is equal to 2.3 millitesla. Then we are asked to find the length of the wire forming the solenoid. So we have to find capital L. Before we find L, we need to find number of turns N first. Why? Because a solenoid is made up of many loops with a circumference of 2 pi r. So we can get L by multiplying N with the circumference of each loop, which will be N is equal to 2 pi r. Why 2 pi r? Because each loop is like a circle, so the circumference of a circle is 2 pi r, with r as the radius. N can be found from B, since we have B. And inside the solenoid, you can find the magnetic field density by using formula B is equal to mu naught Ni over L. And then substitute in all the values to find N. You will get N is equal to 153 turns, and you have to substitute it into the formula of L. So L is N times 2 pi r, and radius is diameter divided by 2, which is 1.3 times 10 to the power of negative 2 meter. And you will get L is equal to 12.5 meter.